So today let us continue our discussions with the decision analysis models. Now particularly today let us cover the decision tables. See, decision tables I have already covered to some detail, and let me tell you, just repeat quickly. Used to represent complex combinations of conditions, actions and rules, used in order to avoid ambiguity, both real and logically impossible, incompleteness, both real and logically impossible, redundancies, and finally the decision table should be put forward in a minimal form. So essentially there are three steps, let me tell you once again. First is the rules, complex rules in terms of logic and all that. Then try to put them into a logical form by in terms of elementary rules, remove ambiguity and incompleteness, and finally put it in a minimal form for easy implementation, right. So we will take further examples, but before that let us go back to that DFD case study. This is the detailed data flow diagram which we have already developed, that is customer to check credit, to check item and to accept order. And let us see the logic which is put forward in these three particular DFD processes, how it is put forward in a decision table example. You can see here that credit worthy, true, items on list, true, items available, true. So when all are true, we send item, right. Similarly, when first two are true and items available not true, then it goes to the pending list. Then in certain conditions, basically where it is not credit worthy or where items are not on the list, right, for those conditions we have, it should be go for a rejection slip. But two conditions are there, basically your actually this y has not come correctly. Actually what has happened, that credit worthy true and items on list false and items available true. This actually is an impossible condition, because the item is not on the list, but how can it be available? There is some sort of impossibility. So there is some ambiguity under those conditions, because once it is credit worthy but items are not on list, so it should show a rejection message, but unfortunately what has happened, the item is available. Now you shouldn't have checked item availability at all, right, but you have checked and you have found the items are available. This is something peculiar, so this is an impossible condition. Similarly, the FFT, that is credit worthy, not credit worthy, item is not on the list, but again item is available. So there are two impossible conditions in this particular decision table example, but otherwise all the things are specified, and these impossibilities one should basically take care. What it should take care, that the items on list and items available, these tables should be matching, right, these tables should be matching. Now let us introduce another new concept, that is known as KMap or so called Carnegie map. See what happens that we are having the rules. Now out of these rules, what we need to do, we need to minimize or put the decision table in the minimal form, alright. Now you can see that if you put it in the form of a decision table, sometimes it could be little difficult. It could be little difficult to put it in the to find out the minimum rule. We have said that the do not care conditions and those sort of things, sometimes it can be complicated to put it in that format. So, what really is done in a KMap is something like this. Let me put you see n and y basically nothing but true and false. So, you can put them as true false as well. See, you can see that let us say there are 4 conditions C1, C2, C3, C4, right, and these 4 conditions, on the basis of these 4 conditions C1, C2, C3, C4. Now, these are our 4 conditions and the action is A. And we have an action called A. Now, let us say that what we have done, see otherwise if there are 4 conditions and each is a binary, then how many do you require? There is 16, you require as many as 16 boxes. So, look at these, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 boxes here, alright. And there is a particular way in this Carnot map that you have to write, we have to put NN, NY, YY and YN. Some of you who are from electronics or computer science background, you already know this, but some others this concept may be slightly new. Let us say that our action is actually in these 2. So, what are the rest? Rest are actually no, fine. So, you basically act only when these 2 boxes are there. Is it okay? How have you got it? Basically the complex logic that has been given, you have applied the complex logic and you have got that when C1 is false, C2 is right, true, C3 and C4 both are true, then you act. Or in other words, you can write the action or decision equal to this is how it can be written. C1 bar means C1 is no, C2 is yes, C3 is yes. Look at these A, C1 is no, C2 is yes, C3 is yes, C4 is yes. So, we wrote it as C1 bar means C1 is no, C2, C3, C4 plus C1, C2, C3, C4. Is it okay? This much is clear to everybody. Now, what we do usually in KMap, you see we have got what is known as a pair. You see, if we get two adjacent boxes filled up vertically or horizontally, we can say that we have got a pair, right. So, we have got here what is known as a pair. Now, what you must remember, if you get a pair, you can remove one variable, alright. So, if you get pair, if you can get a pair, you can remove one variable. So, which variable should you remove? C1. Why C1? Because between these two, look at this, C1 is both no and yes. Please look at this carefully. Between these two boxes, C1 is no as well as C1 is yes. So, C1 is the variable that can be removed from these two, and therefore, we can write the decision as C2, C3, C4. Is it all right? So, this is the basic idea about KMap, but there are more to it. Let us say we have more rays now. So, we have what is known now is a quad. So, let me take another pen. See, there are 4 rays. See, quad may not be formed like this, the quad can also be formed horizontally or vertically. So, we can have an entire row as A's or entire column as A's, or this way also. So, this is the second thing, what is known as a quad. Whenever a quad is formed, you can actually remove two variables. I have said if you get a pair, you can remove one variable. If you get a quad, you can remove two variables. So, what are the two variables that you should remove? C1 and C4. Why C1? Because C1 is no and yes in both these, and C4 because again C4 is no and yes in this particular thing. So, therefore, the quad is actually what is the value of this quad? C2, C3, alright, C2, C3. Then let us go even further. Let us say we have 4 more rays. And all these 4 rays together form what is known as an octet. Right. So, we have 8 A's and we have got what is known as, it has formed an octet, alright. See, it is not that getting any 8 will be enough, they should look like a square, alright. So, or a rectangular shape. So, you see these 8 together form an octet, and how many variables you can remove now? You can remove 3 variables. What are those 3 variables you can remove? C1, C2, C4. So, what remains? So, C3 will remain. So, the value of this octet is therefore C3. What is the value of the quad? C2, C3, and the pair we have already seen C2, C3, C4. Okay. So, you can see that this is how the Karnaugh map analysis is to be done. We have to basically look for pairs, quads and octets. If we can get a pair, we can remove one variable. If I can get a quad, we can remove 2 variables. If I can get an octet, we can remove 3 variables. But let us make it a little more complicated. Let us say along with this we have an additional A here. then how do I put it? Yes, see, actually what we can do, we can make use of overlapping, right? We can make use of overlapping. So, in this case we have got a octet and we also got a pair. So, we can have an octet as well as a pair. So, in this particular case, can you tell me what is the value? Why is so complicated? First you tell me the value of the pair. Yes, pair is C1 and octet so the resulting decision is C3 plus C1 C2 bar C4. So, you see, essentially out of a number of combinations, out of a number of detailed things, we have got all these A's. Then what we have done? We have put it in a simple form, that is C3 plus C1 C2 bar C4. That means in terms of only two decision rules. So, C3 can be put as how C3 can be put? Let us see that, but we will see it as an example rather than individual details. C3 can be shown as do not care at C1, C2, C4 and C3 at true. Similarly, C1, C2, C4 can be shown as do not care at C3 and C1 is true, C2 is false, C4 is true. So, that will be basically our minimal form. In fact, if you go one step further, if you can put it in the form of AND gates and OR gates and NAND gates and NOR gates, you can actually design a logic circuit for this, is it not? You can actually design logic circuits in terms of AND gate, OR gate and all this. So, suppose this is something about a temperature controller of a thermostat, or it is a controller of an electrical machine, then you can actually program a logic gate and put that logic gate as an part and parcel of the controller process. That is what basically one should do in engineering, but since ours is more of application software kind of a situation, we assume that it will be implemented in software rather than in the hardware, right. So, this is about the basic idea of Karnaugh map. Now, let us take one or two simple examples. Let us go back to our original example, simple, very simple in fact. So, see what we have done here, when x is less than 40 then you buy, and when x is greater than 60 do not buy. So, this is what we got in terms of KMap. when both are true, we get both decisions. When only C1 is true, then we have A2. See, this is the KMap. So, this KMap essentially shows two things. What are those two things? First one, this shows ambiguity, and this shows incompleteness, right. So, this is the KMap for this simple example, and the KMap is, I mean, it is also seen in the original decision table, but KMap highlights it in a very nice manner. Now, let us take another example, that is something about and in this example, these are the A1 is why you have TTF, and you have your 1 2 3 1 2 3 yes FTF, and similarly A2 is these ones. Let us take this particular example, alright. So, this one is we have three conditions and there are two actions, alright, and we have not specified action for one or two cases. So, you can see that there are some incompleteness, but more than incompleteness, what we are more interested at this stage is basically finding out the minimal form. So, what should be the minimal form? Try your KMaps, try KMap, and from the KMap try to find out the minimal form. What you can do, because there are three variables, you can take C1, C2 on in one direction and C3 on another direction. So, you can take it like this: NN, NY, YY, YN and NY, C1, C2, C3. So, what kind you have got? Which boxes are filled? You can write A1, A2 on this.
C3 plus C2, C3 bar.
No, first you tell me, out of these which boxes are filled up?
First, all four. So element 1 to A1, A1.
Okay, so this one, no, this one, A1. Next one, A1. Last one, nil. This below all are A2s. You can see that. Now, how do we fill this? By looking at how we have got this decision table from the available thing, whatever is given to us, the complex logic that has been given to us. Then on the basis, this is what we have found out. So, when we have found out this, we can find that A1s form a pair and A2s form a quad, right. So, A1s form a pair and A2s form a quad. So, from this we can infer, since it forms a pair, it can be put in which form? C3 bar and C2, because C1 is both no and yes and C2 is yes in both the cases. So, it is C2 C3 bar, fine. Similarly, A2 forms a quad. So, you can see this is nothing but C3, fine. So, this is what we get, and using this, therefore, it should be possible to put it under a minimal form. Let us see what should be the minimal form. So, you see the action for A1 we have got as C2 C3 bar, and action for A2 we have got as C3. This is what we got from our analysis. Now, therefore, we can write C2 C3 bar. So, C2 is true, C3 is false, and this is do not care, and what we get action as A1, and A2 C3 is true, these are do not care. So, this is the minimal form. Is it okay? So, we started with some kind of a complex logic, and from this complex logic we have tried to put it in the minimal form, right. So, this is the thing that we have the your KMap here, and this KMap analysis shows a pair, therefore, C2 C3 bar, a quad C3, and making use of them we put it together in the minimal form, right. So, I think these two examples have made things little clearer, but still let us take a real example now so that things are even more clear. See, essentially this is about a particular pension scheme. This is about a particular pension scheme. Originally the pension scheme was thought of for a group of people, right, for a group of people. But later on what has happened, as time passed, then increasingly other angle was also important. Say for example, initially the membership see, this is what see, the male and female, basically the word comes at that time everybody was male in this company, no woman employee was there, right. So, essentially male, that is how it was considered, and he should be married, that is because this particular pension scheme was supposed to be for people who are who really require it, right, that was thought at that time due to whatever reason. And an old member, because there was an old pension scheme, anybody who is an old member of the old scheme should be taken, provided he is male and married, right. Then afterwards it was found that many people who did not become old member at that time, and those people are nearing their retirement age, and so increasingly people were thinking that they should be given chance. So, new condition has brought into, that is basically age. So, the new rule, not an old member married and over 40, right. Then some in this time, then they thought that these particular rules, they do not consider anything about females, right. So, let us bring that component also, and for that since there was no old member who is female, so it was automatically thought that it is a not an old member, right, not an old member, but this married condition is put anyway, right. So, that was the third rule. So, this is the third rule, not an old member, female and married, right. Then after this rule, some people, particularly the old employees, they said that there are some people who have not got married, right, but they are quite old. Why should not they get this benefit, right? So, we should give them benefit also. However, since the females are, or women employees are newly joined, there is hardly any need to include them. So, let this rule be specifically for those category of people, male over 40, alright, whether member or not, let us not bother. So, this becomes a rule 4. Right, male over 40. Now, when all these criteria has been taken care of, then some people pointed out that a person who is not an old member, we are given some benefits, whereas the old members are not given benefit. For example, if someone is old member, married and over 40, what will happen, right? So, you see those kind of anomalies, then people thought, okay, forget all these, let us make a sweeping rule. What is this sweeping rule? Anybody who is married will give this facility, alright. So, finally, fifth rule has been made. That just married, anybody if he is married, that is the thing, that he should be member of this scheme. So, you see basically in this particular example, what I wanted to point out is that due to whatever reason, as time changes, new concepts come, new thinking comes, new people join, new management comes, the rules are changing. But usually what happens, rules as such do not change, new rules are added. Sometimes one can scrap also, suppose one can scrap rule 1, possible, but usually this is how things keep on happening, and instead of elementary rules, these rules usually become complex rules, which are combination of lot of elementary conditionalities. Now, if you have to put it in a computer form, in the form of a program or process logic, then it is necessary that you do a decision analysis, alright. So, how should we begin? We should begin by, how should we begin? We should first find out the conditions and actions, right. So, what are the conditions? There are 4 conditions, yes, 4 conditions. Let us write down the conditions. Right. So, this is what is the conditions, and what are the actions? Fine. So, we have decided the membership to new scheme as well as no membership. Fine. Now, see, you can always draw the decision table to begin with. To draw the decision table, how many boxes should be there? There should be 16, because there are 4 conditions and each can have 2 options, true or false. So, we can have 16 combinations and we can specify the actions accordingly. But
We need to specify 2 actions for this, because the other action is just the complementary of one action. So if we get the result for one action.
okay, basically not necessary, but what happens, see, basically you have to see for incompleteness or ambiguity, right. So, one action should be enough, membership to new scheme, but no membership you have also kept, because suppose it is said that if not, deny. See, look at these 5 conditions. What we have said, membership to a pension scheme, rule 1 to rule 5, but we have not said what happens if not. We have not said that. Let us say this now specifically, else. So, else is also a rule. See, these else need not be said all the time. Many of the places the accepted criteria is given, the rejected criteria is not given. Sometimes the rejected criteria is given, accepted criteria is not given. This is also done deliberately at times, let me tell you. Most of the organizations, because they do not know the implications of the no rules. See, if you say else no membership, this basically means that anybody who is not covered under this may still be eligible. See, nobody has seen. So, that is how all these 5 rules have come. But if you say else no membership, then you have also specified that if you have not fulfilled this, you are out. So, many organizations, they do not give an else rule. Fine. So, if you give an else rule, definitely your decision table is complete, because there are some rules, else another rule. But problem comes only when the else rule is not given. Then you may have some incompleteness situations, for which the organization should be given some actions. Now, moment you have given an else rule, it is automatically clear that in our decision table we are going to have complete decision table, alright. So, I am not drawing the decision table because it will be a little too big, that will be around 16. So, I am just putting the KMap, just KMap let me draw of this particular situation. In fact, you try. Right. So, NN, NY, YY and YN. So, this is the thing, C1 is the old member, C2 is the male, C3 married, C4 over 40. So, we have to draw this KMap, and if you really put these rules here, then let me put it in here. Rule 1, an old member, male and married. So, old member is C1, male is C2, C3. This is rule 1. Rule 2, not an old member, C1 bar, married, that is C3, over 40, C4. Rule 3, not an old member, C1 bar, female, C2 bar and married, that is C3. Rule 4, male and over 40, so C2, C4. And finally R5, that is C3. Fine. So, this is the thing. Now, we have to specify the actions on this particular case. So, first we begin with C1, C2, C3. So, what are the things? C1, C2, C3. C1, yes, is this. C2, yes. C1, C2 both yes is this, and C3 also yes is these two. Is it okay? Fine. So, these two we write A1. Then C1 bar, C1 bar means this, and C3, C4. So, these two, isn't it? Fine. C1 bar means where C1 is no and C3, C4 both are yes. So, we write A1, A1. Then the third rule, where C1 bar and C2 bar, that means both are no and C3 is yes. So, actually these two. I am sorry, these two. Already one A1 is there, so another A1. Then C2, C4. C2, C4 is a quad kind of a thing. So, C2 is yes here, yes here, and C4 is yes here. Is it okay? So, these four. This is C2, C4, and finally C3 yes will make all these as A1. Is it okay? Fine. So, you can think about it, how we have got this particular logic. You can see that there are a lot of overlaps here. So, let me just put it once more. C1, C2 yes is this, where C3 is also yes. So, these two, fine, these two. Then C1 bar and C3, C4 is these two. Then C1 bar, C2 bar, C1 bar, C2 bar. So, NN this isn't it? This, and then C2, C4 is this one, and C3 is the whole thing. C3 is this whole thing. Is it clear? So, you can see that between these decision rules there are so much of overlap. Because of this overlap, usually we may have difficult situations, and because they are actually complex logics. So, what should we get now? We simplify, very easy to simplify. We have a octet and we have a pair, or you can say it is a quad, I mean up to you, you can put it as a pair also, but okay, if you want it that way. So, you can have an octet. So, the octet is this one. What is the value of the octet? C3. What is the value of the quad? C2, C4. So, you can see that all the other rules actually are become redundant. So, we have the action equal to C3 plus C2, C4, right. So, we can quickly put it in the form of a C2, C3, C4 ensure. So, so what do we get? C3, that is true, don't care, and C2, C4 is true, don't care, true. Fine. So, this is the minimal form. So, what has happened in the minimal form? That we have been able to remove one condition C1, that is old member or not, we need not check even. C3 true, member, make him a member, C2 true, C4 true, C3 don't care, make him a member, else no to membership. So, this is the minimal form and we can use these rules only as per the present situation. Is it okay? So, this is about the decision tables. I stop here today, and there are some more things about decision analysis which we shall discuss on Thursday, Wednesday.